Welcome everyone. Today's topic is estimators. And in terms of what we're doing, the roadmap of the course, we've just finished the entire section on probability theory. And to be honest, the only purpose of that is to get us to be able to understand the stuff that we're going to cover in the next few weeks. So that's all kind of a prerequisite material. And so if that seemed kind of like abstract, why are we doing this? Now is when it's going to start to meet the road a little bit, and you're going to see what is the point of statistics and why did we need to build up all this language and concepts of expectations, distributions, independence, and whatnot. Because all the stuff that we're going to talk about applying statistics to the real world is going to have us formulate our assumptions and our questions in terms of that language. So the topic today is estimators, and the entire idea is how do we guess what we want to know about the population when we only have some small sample, some data set that we observe. We don't get to see the whole population. So how do we guess what we want to know? So that's illustrated here in this picture. So on the left, we have our little conceptual data generating process, which again, you can think of as a population data set if you want, a very large population data set, or some density function distribution, or some like R code that you press go and it gives you a sample of data, and you can press go again and it'll give you another sample of data. So however you want to think of that, they're all equivalent, okay? So that's on the left of this dotted line, which is stuff that we can't see. We cannot fundamentally observe it or touch it or feel it or anything. What we can see is what's on the right, or I don't know what side of the screen it is on for you, but this little analyst guy over here and the data that we see. So this is a finite data set of n samples. Usually each row is a person, for example, and the columns are different measurements about the people, and that's what we get to know. That's it. But what we're interested in is really something about the population, right? We don't care specifically about, how the average height of these 10 people. We want to know the average height in the population, or like the prevalence of COVID in the population. We don't care about the 10 people we observe, really. I mean, we care about them, but we care a lot more about everyone else as well. So that's the issue, right? How do we do this magic? And there really is no magic here, and we're gonna see that. But the question is actually what's really the best we can do? How can we at least quantify our uncertainty, given the fact that we don't get to see what's over here? And so let's get into that. How do we guess, right? What is it that we do with this data to guess about what's over here? So a lot of this stuff you've probably actually seen before, at least glancingly. So this is, I think, the same abstract or paragraph that I showed in the last lecture when I was talking about expectation. So, with expectation, we can build up these estimands, things like the conditional risk ratio, define exactly what we mean by effect modification, marginal risk ratio. And these are all specific things that we didn't necessarily talk about, but some of them we'll talk about later in the course. But they're all of these things are just expectations or conditional expectations of one thing given another, or the difference of two conditional expectations, things like that. Now, the other things that I've highlighted in red, these are, these three here, these are estimators, okay? So these are methods, they're algorithms that people apply to data sets in order to guess the value of these estimands, all right? And I've also highlighted these other words here, biased and valid, because we're going to talk about a bit today about what does it mean for a method to be valid or biased? What's the precise meaning of those terms? And more generally, how is it that you can judge an estimator? Like if I give you an algorithm that you give me data and I give you an algorithm and I say, this is what you have to do to the data in order to get your answer. How does that in any way guarantee that your answer is good or bad? Or how can you, if somebody else gives you a different algorithm, how can you compare them, at least conceptually, to say that one might be better than another, or under what conditions might one be better than the other? All of that is stuff that right now you can only really hand wave about, but using the language and the tools that we've built up earlier in the course, we're going to see how it is that we can make those things concrete and precise, and be able to solve the real world problems of, okay, you have a data set, what do you do with it? So big picture here, estimators. What is it? It's an algorithm or a method that turns data into a number. Okay, and that number is your guess to try to answer whatever question you have. So let's look at an example. So here we have a data generating process, and in this example, I'm saying x is some normal variable. So I'm measuring two variables basically, x and y, and x is normally distributed and y is conditional on x, also normally distributed. But I don't know that. Okay, here I'm just giving you the example so that you can see, like, if you're God, this is what you would see, right? I don't know that, but what I do know is that I'm interested in the marginal variance of y. So maybe y, for example, is some biomarker, and I want to know how variable in my population is this biomarker. Is it the case that most people all have the same value of this biomarker, or is there some variability? Because if there is, then maybe that's being caused by some underlying disease where some people are, like, the healthy state is a low level of this biomarker and the disease state is a high level. I don't know. So what I'm trying to figure out is, what is the variance of this biomarker in the population overall? And let's say that the number I get, which you can compute, again, if you're God, you can look at this, if this is the actual data generating process, you can just do your rules of expectation and blah, 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 or, plug it into Wolfram Alpha and compute whatever integrals you need to compute. And you'll get this number, 3.25. But we don't know that, right? We're over here on the other side of this wall, and we don't know that the right answer is 3.25. What we do get to see is this table of data. So let's say that I sampled 5 people from this population. And again, what I'm interested in is, and this variable y is their biomarker level. And I want to know, what is this population variance? But I only have these 5 people. Well, what can I do? One sensible thing is to take the sample variance. So I can put this data in R and I can call var y, okay? And that is going to give me a number. That's this number here. For this data set, this is the number I get. So this var function, that is our estimator, because that's the thing. We're putting the data into it and it's giving us back a number, okay? So the sample variance of y is, for some data set, is an estimator. And in this case, the answer we get is 0.66. And you might look at this and say, well, that's kind of shitty. That looks nothing like 3.25, right? That's like an order of magnitude off. Yeah, that can happen, right? So maybe there's a better way that we could have tried to guess what this number is, or maybe there isn't. Maybe it's just we got a bad data set, right? And if we had sampled again, we would have gotten a closer number. And so the whole point of thinking about estimators is understanding, well, which of those two is it, right? Is it some property of the estimator, or is it up to luck, or how do we distinguish what's going on there? So let's look at another example, risk ratio. So here's a more complicated data generating process. Again, this doesn't really matter. I'm just showing you this so that in theory you could compute this true number. But in this case, I'm interested in something called the risk ratio. And I can't remember if we've glanced on risk ratios before, or I've shown you the actual definition, but it's this. So if you have a binary, usually is y, we call it an outcome, and W here is an exposure of interest, the risk ratio is defined as this. So it's what's the value of y I expect to see among the people who are exposed relative to the value of y I expect to see for the people who are not exposed. So if this number, the top number, is bigger than the bottom number, then my risk ratio is going to be positive. And that indicates that the outcome I expect to see is on average bigger for those who get exposed, right? So if the outcome is a bad thing, if this number is big, then is bigger than 1, then that's telling us that this exposure is associated with an increased risk of the outcome. Whereas if it's less than 0, it's decreasing the risk of the outcome. And I mean, this is not like a core component of this course. You'll learn more about this in your epi courses and how to interpret these things and so on and so forth. I'm just showing you it as one example of a thing that you might be interested in figuring out, right? So, for example, like if W is exposure to some kind of a toxic chemical, and you want to know, does this affect the birth weight of children, right? Or does it not? Or at least what's the association there? This is one way to measure that. Okay. So let's say that's what we're interested in. Again, here, since I know the true data generating process, in general I don't, but since here I've written it down for you, you can do the math. You don't have to because I did it for you. And I'll tell you that the value of this thing here is 1.394. Now here, again, same thing. We don't get to see this. All we get to see is some sample. And in this case, I have 100 observations. And the question is, what do I do? What do I do to guess what this number is? And so what I've done, I've written some code. And my code splits up the data into groups, W equals 1 and W equals 0 groups. So the exposed people and the unexposed people in the data. And then I just take the average value of Y in both of those groups. And then I divide it. So I'm basically doing this, but instead of with the population data, I'm doing this with the sample that I have. And I'm saying, well, okay, that's going to be my guess, is whatever value comes out of this in my sample. And you can see, yeah, they're different, but in this example, they're actually pretty close. So here, this code is the estimator, all right? This is the estimator. So this is using the data. You start with the data, and at the end, you get a number, all right? But I could have done this, differently. Maybe here I put something else. Instead of taking the average of Y in each group, I take the median and I divide that. That's going to give me a number. But is it the same as this? Is it better? Is it worse than this code? That's what we're going to talk about. So, and something that I don't have on this slide, but I wish I had is this data is random, right? If I did this again, I repeated the exact same experiment. I use the exact same code here. This were the exact same data generating process. This hasn't changed, but I just repeated the experiment. That is, I get more data. I get a different data set. If I plug this data into this code, the new data into this code, I'm going to get a different answer. So the value of the answer I get is random. And what I mean by random, whenever somebody says something is random, it just means it depends on the data. And the data depend on who you get in your sample, which is random. You don't know before you run the experiment who you're going to get. And so this number is not fixed. This number is fixed. This is a population quantity. This number is going to vary, and we'll talk a lot more about that. Okay, so a little bit of notation here. This picture, I've just kind of abstracted it. So let's say that you have some data, and they're drawn from some distribution. Here I'm writing Z as a univariate thing, but you could imagine that Z is actually like X, Y, Q, R, whatever. So this is some joint distribution. So your random variables are jointly distributed according to some distribution. The estimand is some function of that distribution. So it could be an expectation, it could be a probability, it could be a variance, it could be a ratio of expectations, whatever it is. It's a function of whatever this density is, right? Because when I take, for example, an expectation, if I say, what's the expected value of Z? Well, that depends on how Z is, what the distribution of Z is. So this is this kind of notation just says, you define what the expectation is, or what the variance is, or whatever of what variable, but then it depends on how this variable is distributed. You're going to get a different answer, which is to say, like, if let's say you want the average age, well, if you think of the probability distribution as like what population you're talking about, well, of course, like the average age is going to vary by population. So that's kind of what this notation is trying to express, is that the value of the estimand depends on the true probability distribution, but that's something that's fixed. You don't know it, but it's fixed. Okay, so what do we see over here? We get the data. So here I'm notating that with capital Z, 1, ... n. So these are the n rows in your data set. And what we want to do is guess what this value over here is. And so we put that data through what is we call an estimator. And the estimator we denote with a hat. So the estimand, the value we want to know, I went generically, I'm going to call it psi, this psi here. And then a generic estimator, I'm going to say psi hat. So when we put the hat over something, and different people use different notations, so but generally you might see like, oh, I want to estimate, let's say this distribution is, normal. I'm assuming that this is some normal distribution, okay? And then this thing here, what I want to estimate is the expected value of Z, okay? For example, the expected value of Z from a distribution, some normal distribution with mean mu and standard deviation sigma is just going to be mu. So the thing I'm trying to estimate is this mu number. And so the estimator, whatever estimate I get of it, I'm going to call mu hat. All right. So when you see the hat over something, it generally just means this is my guess of whatever thing is being hatted, and then that thing is defined, in reference to the population. So this estimator is some function that takes the data and then returns this guess. Okay, so you can write it like this if you want, where it's a function of the data, which makes it clear that this is random. So this is the main idea. If you want to get away from all of that notation, that's just some detail so that if you really want to think it through, you can see it that way. But the really main idea that you got to stick in your head is that this psi thing, or whatever letter or thing that you use to notate it, is this represents the estimand. It is some fixed number. It's what we want to know about the population. Okay. The thing on the right, this estimate, the psi hat, that's our guess based on data. So hopefully you're understanding this. I've repeated it a lot of times, but that's because it's really important to get that this thing is a guess and that this thing is a fixed number. We don't know what it is, but you have to imagine it's there. It has some value. Okay, so let's do another example here. Let's say I collect data on vaccine hesitancy, and I measure that. I survey people, and I measure their hesitancy to get a vaccine in terms of like this Likert scale, 1 to 5. So 1 is low hesitancy and 5 is high. And I have enough money to go talk to 10 random people in San Francisco, and these are the numbers that I get: 1, 3, 3, 2, 1, 4, 2, 1, 5, 1. What I want to know is the population average vaccine hesitancy for everyone in San Francisco. I only have these 10 people though, right? So my question to you is, which of these down here is a better guess of the population number based on these data here? So the first one is, well, I could take the sample average of these data, and if you do that, the number you get is 2.3. Or I could say, you know what, I trust the first person that I talked to more than I trust everyone else, so I'm just going to take that number 1. And then the next one is, I'm going to trust my friend who's a domain expert who's been studying vaccine hesitancy for many, many years, and they think the number is 1.5. They haven't even looked at these data. They just think the number is 1.5. And then the last option here is, instead of taking the sample average of this data, I could take the sample median, and in this case, it's 2. And I'm interested, again, in the population average of these numbers if I had sampled everyone. So which of these is a better guess? There's no right answer here necessarily, right? The idea is for you to kind of think about it. So you can't know, right? Unless you know the truth, right? So we have to have some kind of like truth agnostic way of measuring what is a good or a bad estimator. But even without that, let's say we can say some things about this, right? So the sample average, I know that since I only have 10 observations, that number could vary wildly from sample to sample, right? And for example, like let's say instead of 10, I had 5 observations, right? And let's say I had gotten these 5, 1, 3, 3, 2, 1. The sample average of that is 2, versus the sample average of these last 5 numbers is 1, 1, 4, 5. So it's going to be 2. Yeah, this one it's going to be a little bit higher than that. Specifically, it's going to be 6, 7, 12, 13 over 5, whatever that is. So it's a bit higher than 2. And so there's variability in this number. So maybe this is not a good estimator because it's not going to be very consistent if I were to repeat it. Okay. Whereas my buddy's guess, this domain expert, they didn't even look at the data. So it doesn't matter what data I got. They're going to get the same answer every single time. So this estimator is consistent in the sense that it's not going to change, right? Whereas this one does. Is that good or is that bad? Well, it depends on what the right answer is, right? Maybe this estimator is bad because the right answer is let's say the right answer is 2.5 in the whole population, right? Then this would be a bad answer because it's always going to be off by 1, right? Whereas this, maybe it's variable, but on average, you're going to be getting something close to the right answer. And so maybe this is on average better than this, right? So these are the kinds of ideas that we're going to get into a little bit more concretely. But for now, I think it's useful to address them in this heuristic way. So here's another question. Let's say I run 6 identical surveys and I get different samples. So it's like this, but I do this process 6 times. And for each survey, I analyze the data in 2 different ways. So I compute the sample average of the responses that I got, and I compute the sample median of the responses. So these are 2 different estimators, right? They're each giving me a number that I'm going to treat as my guess of the population average, even though neither of them really is, but it's my best guess. And I want to see, well, okay, which of them is a better guess or a worse guess. So let's say that the sample averages I got were 1, 2, 3, 3, 4, 5, and the sample medians were 2, 2, 2, 2, 3, 3. So again, what's better depends on what the right answer actually is, of course. So let's presume that the true population average is 3. So which set of guesses is better? How do you assess how good each strategy is, right? So in this case, maybe you could say, okay, the average guess here is 3, right? So across all the samples that I got, the average guess is 3, so that's good, right? Down for this one, the average guess is a little less than 3. It's actually closer to 2. And so that's bad. However, this thing is more, again, like the example we talked about here, where your buddy is always guessing the same number. This thing is more consistent, whereas here the guesses vary wildly. So I get a guess of 1 in one case, and I get a guess of 5 in another case. And in reality, you're going to only do this experiment once. And so if I'm telling you that there's a pretty good chance that you're going to get a number that's wildly off, do you want to do that? That's not good, right? Whereas down here, you're never going to get a number that's wildly off, but all of your numbers will be slightly off. So which do you prefer? And again, there's not really a right answer, but these are the kinds of questions we'll learn how to handle concretely.